Okay, I invited you to draw the curved arrows of this mechanism ahead of time to see how you did there, and so let's work through it here. So again, you could have drawn out the mechanism on your own, the 5-step mechanism to form the CN um, double bond right there. And this compound that it's reacting with, that looks like some sort of primary amine with a nitrogen on it, is called hydrazine. And when a hydrazine reacts with a ketone, then the product that is formed here, this looks like an imine but it has a nitrogen on it, is referred to as a hydrazone. So it's a hydrazine reacting with a ketone gives a hydrazone, which is somewhat logical. Okay, so we have a strong base that is present, that is dumped in with the hydrazine, and so we have this strong base, and it could pull off an acidic hydrogen. And if we look at the product of this step, it has hydrogen has been removed, and so the base would come in, form a bond to that proton there, and the electrons would dump in here, and there was already a lone pair here, and now we're putting a second lone pair. So a nitrogen with 2 bonds to it and 2 lone pairs has a negative charge. So we have deprotonation has occurred in that step, so we can label it that. Then what happens in the next step? So there is a double bond to nitrogen from this carbon here, and now that is converted into a single bond to nitrogen, and we have a hydrogen there. So where did that hydrogen come from? We also have there's a single bond here, and now it's a double bond. And so we have a single bond that is converted to a double bond, and a double bond that is converted to a single bond, and then a new sigma bond here. So a lot of things going on. And we have water that is a reactant. So first thing we notice here, if we're putting in our lone pairs here, is we had 2 lone pairs, and now we only have 1. And so one of those lone pairs has disappeared, and so it seems logical that the new pi bond that is formed here came from that lone pair. So if you draw a curved arrow there, that kind of makes sense. And then we have a lone pair on nitrogen, and if we just dump that in there, we have 4 bonds to nitrogen plus a lone pair, which would be 5 lone or 10 electrons around nitrogen, which is not possible. So as we're bringing in electrons, we're taking away electrons, and so we can break this pi bond and dump the electrons onto that carbon. And then we end up with a hydrogen on that carbon. So let's pick up this proton here off of water and dump and add the proton onto the carbon. So this is kind of the equivalent of, this is very basic because it's got a negative charge on it, and this is somewhat acidic. It's neutral water, but it can act as an acid. So we could have added the proton directly onto the nitrogen, but that nitrogen, that lone pair, is also spread out by resonance onto the carbon, and so it has gone here. This is nothing that we would have predicted, okay? This is, in the end, we know that when you go in the lab and you dump this and this together, you get this. The question is, how did it get there? And if you were trying to figure out the mechanism, you know exactly what you would do. You'd figure out all the bonds that were broken and the bonds that were formed, and then you try to figure out how to get there through breaking and forming bonds. And so what we need to be doing is adding hydrogens onto this carbon right here, and those hydrogens have to come somewhere from the reagents that we have added. Okay, so here we are. again, and we're getting closer, trying to get closer to where we need to be with another hydrogen here, and we've already been told that nitrogen gas is formed here, which has a lone pair on both nitrogens. And so we would have to get rid of the hydrogen, and we'd have to break this bond. So if we have a base in there, then again that base, like it did in the previous example, can pull off this proton. The electrons can dump in here, which would make too many electrons around nitrogen, and the electrons then would be kicked out and end up having a lone pair or a carbanion on the carbon there. And it's already got one hydrogen on it, and as we did before, we can pull off a hydrogen off of water, regenerating the hydroxide, giving the final product. And so we said this first step was deprotonation. What has happened in this second step? We started out with 1 pi bond, we ended up with 1 pi bond. What have we done? Well, this whole thing here has, basically all we've done is pull H plus off of water and dump it onto this species right here. So this is acting as a base, and water is acting as an acid, and so this is an acid-base reaction. So it's an acid-base reaction, or if you're just looking at it from the perspective of this base, it is a protonation because we've added a proton we've added this hydrogen on there. Okay, so then the next step here, what is going on? Well, all kinds of crazy things going on. We've got more arrows than we typically draw in one step. But the important thing is you see that you have a carbon or nitrogen-nitrogen double bond, which has become a triple bond. So if we're gaining a pi bond, if we're forming a pi bond in the reaction, what is it called? If you said elimination, good for you. Okay, forming a pi bond in elimination. And then we end up with this species here, which is acting as a base, pulling off a proton there. So we're protonating this. It's an acid-base reaction. This is the acid, and this is the base. And so we're adding a proton onto the thing that we're interested in, so we're going to call that a protonation. Just an interesting mechanism, tying in and kind of using the principles that you have been taught over the previous few weeks for drawing mechanisms and using curved arrows. In the end, this is just a nice tool for getting rid of a carbonyl if you need to, and the reagents are hydrazine and hydroxide. Sodium hydroxide. You dump those two in together and heat it up, and there you go. Voila. Wolff-Kishner Reduction. And as you might suspect, these are the last names of the guys that discovered this reaction.